Hi everyone. So in today's video, we are going to go over this paper, Quantifying Memorization Across Neural Language Models by the team at Google Research, University of Pennsylvania and Cornell University. So the authors are Nicholas Carlini, Daphne Ippolito, Matthew Jagielski, Catherine Lee, Florian Tramer, and Xuan Zhang. I'm really sorry if I mispronounced any of those names. All right. So getting right into the abstract, large language models have been shown to memorize parts of their training data, and when prompted appropriately, they will emit the memorized training data verbatim. This is undesirable because memorization violates privacy. So if there's any data leakage in the training data, data leakage in terms of like personal data, it will be there in the model, exposing the data, degrades utility. The repeated, easy to memorize text is often low quality and hurts fairness. Some texts are memorized over others. So we describe three log linear relationships that quantify the degree to which language models emit memorized training data. Memorization significantly grows as we increase the capacity of the model. The number of times an example has been duplicated, and the number of tokens of context used to prompt the model. Surprisingly, we find the situation becomes complicated when generalizing these results across model families. On the whole, we find that memorization in language models is more prevalent than previously believed and will likely get worse as models continue to scale, at least without active mitigation. So the paper basically tries to show uh, what is memorization. They give a definition of memorization. Why is it bad? Is it always bad? That has also been explored in subsequent works. I'm not sure if this work explores that, but and how is memorization influenced by factors like the model size, how many times the data point is seen, and so on. All right. So for the introduction, the performance of neural language models has continuously improved as these models have grown from millions to trillions of parameters with their training sets similarly growing from millions to trillions of tokens in the anticipation of future, even larger models trained on minimally curated datasets. It is important to quantify factors that lead to increased memorization of a model's training set. So why do they say minimally curated? I guess this is because at some point when you're dealing with trillions of tokens, there's no way you're going to be able to curate the data sets very precisely because at that point you're sort of reaching the ends of just scraping everything, right? So I guess that's why the curation, like it's minimal. Indeed, recent works have shown that training data extraction attacks are a practical threat for current language models. An adversary interacting with a pre-trained model can extract individual sequences that they use to train the model. So this in some sense is like finding out what the model memorized in some sense. While current attacks are effective, they only represent a lower bound on how much memorization occurs in existing models. So, for example, by querying the GPT-2 language model, Carlin et al. Manually identified just 600 memorized training examples out of a 40 GB training dataset. This attack establishes a loose lower bound that at least this small value of the data set is memorized. The small value percentage of the data set is memorized. In contrast, we are able to show that the 6 billion parameter GPT-J model memorized at least 1% of its training data, which is the pile training data. So the pile training data is, I believe, around 850 gigs or somewhere around that sort. So 1% of that is 8.5 gigs, which is a huge amount. So now you know why this is important. So in addition to these loose estimates of models' memorization capabilities, there is a limited understanding of how memorization varies across different neural language models and data sets of different sizes, different scales. So prior studies of memorization in language models either focus on model or dataset of a fixed size or identify a narrow memorization versus scale relationship. So these are like the challenges with the current works. They either focus on models or datasets of a fixed size or identify a narrow memorization versus scale relationship. So McCoy et al. Broadly study the extent to which language models memorize, but their focus is on how to avoid the problem and ensure novelty of a model's outputs rather than on studying the risk through identifying maximum memorization. So their point was not to identify how much can they find out has been memorized, but rather to figure out ways to evade that. This paper addresses both of the above open questions by comprehensively quantifying memorization across three families of neural language models and their associated datasets. We leverage access to each model's original training set to provide order of magnitude more precise bounds on the amount of extractable data than in prior works. To construct a set of prompts from the model's training set, we feed varying length prefixes of the training data back into the model and verify whether the model is able to complete the rest of the example verbatim. This allows us to measure memorization across all of these things and identify some properties which significantly impact memorization. So, a model scale, larger models memorize 2 to 5x more data, data duplication, examples repeated and more likely to be extractable, and context. It is order of magnitude easier to extract sequences when given a longer surrounding context. So all of these intuitively make sense. You would expect a larger model to have more capacity to sort of memorize things, and then uh, things which are seen more often are more likely to be memorized. And then, in terms of context, the more hints you give to the model, it's more likely to spit out verbatim what it saw in the training time. Our analysis suggests that future research in neural language modeling will need to take steps to prevent larger models to memorize. Alright, so related works. There is extensive prior work that qualitatively studies memorization in neural language models, even constrained to just extraction. Prior works has demonstrated that it is possible to recover various forms of memorized data, including URLs, phone numbers, and other forms of personal information, or in other works, synthetically inject canaries. However, most of these works are qualitative and aim to demonstrate the existence of extractable data rather than precisely quantify how much the model memorized. For example, the unprompted memorization evaluation of Carlin et al. Found 600 examples of memorization. A paper aims to establish much tighter approximations to the fraction of a dataset that can be adversarially extracted. Our analysis is relevant to the broad literature on privacy attacks on machine learning. For example, membership inference attacks allow an adversary to detect the presence of a given example in the model's training dataset, and other forms of data leakage permit an adversary to learn dataset properties. We focus on extraction attacks due to their relevance for language modeling. Extraction demonstrates significant leakage from a model and grows with data duplication, a common feature of large-scale text datasets. So, big datasets have lots of duplication because you would assume popular things are cross-posted across websites and so on. Then various formulations, memorization, and deep neural networks have been studied in previous papers. A detailed comparison with those is present in section 3.1. One leading general memorization definition is differential privacy, which is formulated around the idea that removing any user's data from the training set should not change the trained model significantly. However, while differential privacy protects a single user's private information, it is ineffective for memorization of duplicated data and does not capture the complexity of social linguistic data. Also, differentially private deep learning algorithms generally suffer from expensive computation, slow convergence, and poor model utility despite recent advances. So this is just comparing, like showcasing what exists in the differential privacy literature and how is that different from what they do. Concurrent work, Nikhil Kandpal studies how often models will, without training data prompting, emit memorized data as a function of data duplication. This analysis focuses on evaluating why training data extraction attacks succeed. In contrast, this work focuses on a setting where they prompt the model explicitly with training data in order to measure the worst case setting, something that a practical attack would not do. All right. So prior scaling hypothesis, our motivation to scale scaling phenomena comes from the anecdotal evidence in prior work that memorization ability relates to various aspects of scale. In particular, our analysis on model scale is informed by preliminary experiments in Zhang et al. And Carlini et al. Our data duplication experiments following the line of Lee et al. And our context-linked experiments are built on hypotheses by Carlini et al. And Ziegler. All right. So I guess we're done with the works which I mentioned, or the broad areas of research which are related to memorization. Now let's go over the methodology. What is memorization? In all, so how does X impact memorization? To answer this question, first you need to know what is memorization. So their definition is a string S is extractable with k tokens of context from model F if there exists a length k string P such that the concatenation PS is contained in the training data for F and F produces S when prompted with P using 3D decoding. So this might seem like a mouthful, but this is pretty simple. What they're basically saying is that you have a string S and it is said to be extractable with k tokens of context from a model F if there is a length k string P. So P is of P are the k tokens of context which I referring to above. And once you give that string P as a prompt, you get this string S as the output, and then when you concatenate P and S, you find that this entire string is present in the training data. And another thing, interesting thing is that they are only constrained to greedy decoding. So basically, what does the model associate the highest probability with? For example, if a model's training dataset contains this example and given the prefix this, th- the most likely output is the number which was there in the original training sample. Then this is a extractable sequence with 4 words of context. They focus on greedy sampling and verify that a choice of decoding strategy does not significantly impact the results. While prior work uses other definitions, we prefer our definition for several reasons. It is more actionable. There is a class of memorization definitions, including lower bounds on differential privacy or counterfactual memorization, which require training data of hundreds of thousands of models to ensure privacy, making them impractical for evaluating enormous language models because you can't have hundreds of thousands of such models. All right. So prior definitions of memorization have additional weaknesses. Computing exposure requires thousands of generations per sequence and is designed for carefully crafted written examples, making it computationally infeasible for large-scale examples. Additionally, k-eidetic memorization is a useful definition for unprompted memorization, but less useful when prompting with training data, as is the case in this paper. So they're not claiming this definition is better for arbitrary privacy measurement studies. We use this definition in this paper because when given access to a model's training data, extractable with k tokens of context is a helpful and precise definition. In future works, you can use these three scaling law observations to other memorization definitions as well. Alright. So selection of evaluation data, having chosen a definition, then they need a way to evaluate. Ideally, they would want to consider every sequence, but this would be very computationally infeasible. So, just for example, they've given analysis. If you take the largest 6 billion GPT Neo model and assume that it has a throughput of 100 token generation per second on a V100, so if you take the entire 800 GB of file, it would take 30 GPU years of compute. And like if you say, okay, I'll take 10 of those, maybe you reduce this if you do not achieve any losses. When running them in parallel, maybe you reduce this by 1/10, but then it's still 3 years. You can't. It would be highly impractical to do that. Instead, they query a small subset of the training data. This subset should be small enough that it is feasible, but also large enough to give them statistical confidence. In this paper, they choose subsets of roughly 50,000 sequences. The primary criteria when choosing a subset of the training data is to obtain a representative sample that allows us to draw meaningful conclusions from the data. Yet naively sampling from the data independently at random to construct a representative subset is not the best approach. Indeed, prior work has identified that one of the most important factors uh, that contribute to training data memorization is how often the data has been duplicated, because the frequency of training data duplication follows an exponential distribution. A fully random sample of 50,000 sequences, accounting for less than 0.02% of the dataset, is unlikely to contain any signal that would allow us to accurately measure the tail of this distribution. So this is why you can't just randomly sample points, because then you'll be missing out on the uh, tail ends of the distribution, because some of the samples would be very very frequent, and some would be just appearing once, and then those appearing once would have a much lower chance of being picked. So instead, they construct a duplication normalized subset. So they take the sequence lengths and an integer n. They select 1,000 sequences of length L that contain that are contained in a training dataset between 2 to the n by 4 and 2 to the n plus 1 by 4 times. So for length 50, they have 1,000 sequences which are contained these many times. They do this until they reach an n for which 1,000 sequences are not available. This gives us 1,000 sequences that repeat between 6 and 8 times, and also 1,000 sequences that repeat between 724 and 861 times. This bias sampling allows us to more accurately measure memorization as a function of sample duplication factor without querying the entire dataset, because they now know which samples were seen more frequently as well in their subset. Note that constructing this duplicate normalized data subset requires some work, as efficiently identifying duplicate strings in 800 GBs of training data is computationally challenging. So in their case, they make use of a suffix array construction. So for each sequence length between 50 and 500 tokens, this collection process gives them roughly 50,000 examples, duplicated varying number of times, totally roughly 500,000 sequences. So for each length L sequence, we prompt the model with the first L minus 50 tokens and then report the sequence as extractable if the next 50 tokens are an exact match. 50 tokens correspond to an average of 127 characters or 25 words, well over the length of a typical English sentence. Finally, they compute the average probability uh, that the sequence is extractable by averaging over all lengths L. So now we come to their experiments. We are now familiar with what their methodology is. They're using the GPT-Neo family trained on the PILE dataset. So if you're wondering why they did not use the Pythia models, well, this paper came out before the Pythia models were made public. I guess even before the Pythia models were started to be trained. So you can see why they did not. So the GPT-Neo models are, of course, the language models trained with the objective of predicting the next token. They come in four sizes. So you have 125 million one, a 1.3 billion, 2.7 billion, and 6 billion parameter models. The pile is a dataset containing text collected from various sources. So you have books, websites, etc. that total 825 gigs. The largest GPT-Neo model is the largest language model available for public download, and the pile is the largest public text dataset. All right. So bigger models memorize more. I guess the title gives it all away. Shouldn't they have like a spoiler warning? So we begin by considering the impact of model size on memorization, expanding on prior studies which qualitatively establish a relationship between the size of GPT-2 and their ability to memorize URLs. In contrast, they study a million model generations in order to describe how scale relates to memorization. So the results are shown in figure 1a. The y-axis shows the fractions of generation which exactly reproduce the true suffix, average over all prompts and sequence lengths we experimented on. We find that the larger models memorize significantly more than the smaller models do, with a near perfect log linear fit. A tenfold increase in model size corresponding to an increase in memorization of 19%. So let's just go to figure 1a. Was this the first figure in the paper? Right. Okay. So 1A, we prompt various sizes of GPT-Neo green with data from the training set. As a baseline yellow, we also prompt the GPT-2 family of model with the same pile-derived prompts, even though they were trained on web text. So this just shows you that the baseline is you cannot extract those pieces of text. Basically what the model was not trained on, it was not able to, the experiments were not able to extract that from it. But in this plot, you can see that as the model size are becoming significantly larger, the fraction extractable is becoming big. Also, this is a log linear scale, as you can see. So otherwise you wouldn't have 120 million and 6 billion on the same scale with like steps of uh, what 345 minus 120 to 25 million. Yeah, so you can see this is a significant increase because this is not a linear, this is a log linear plot. To confirm that larger models are indeed memorizing more data and not simply generalizing better, we also perform the same analysis with GPT-2. The GPT-2 family of models are similarly sized and also trained on internet scrape. If our larger models memorize more, results were due to general predictive trend of the larger models and not the memorization of specific training data. We would expect a similar relationship in GPT-2 as well because it was trained on similar data and not memorize and uh, because open web text is also like all of the a lot of the web. Put differently, this baseline allows us to establish what fraction of the training data is easy enough to predict. That any language model correctly could predict the 50 token suffix even if the example had never been seen before. For example, a language model that has seen multiple examples of number sequences could learn to correctly complete other types of sequences. We find approximately 6% of the examples in our evaluation dataset can be correctly completed by GPT-2, while 40% for a similarly sized 1.3 billion GPT new model. So this is a big jump. And if you look at a qualitative analysis, which we do in Appendix Figure 13, you see examples memorized by GPT-2 are largely uninteresting sequences. Therefore, they conclude that larger models have a higher fraction of extractable training data. It is because they memorize the data. It is not simply because larger models are generally more accurate. Alright. Now, are repeated strings memorized more? Right. Sorry about the abrupt cut. If you notice the time, maybe the time did not change. I just have to sneeze. Right. So repeated strings are memorized more. Again, a spoiler. Please don't do this. Joking. So prior works have provided preliminary evidence that memorization language models increase with the number of times sequences are repeated. We expand on this observation and systematically measure the effect of number of repetitions on memorization. Using the experimental methodology, we measure the fraction of sequences that are extractable for sequences in each of the different buckets. So some having as low as 2 duplicates and some going as high as 900 duplicates, with each bucket having 1,000 distinct sequences. And we compute the average amount of memorization for each bucket. So again, let's first go to figure 1b and observe stuff for ourselves. So examples that are repeated more often in the training set are more likely to be extractable following the log linear trend. So you can see as the data repetition goes up, your memory extractability goes up in some sense. So interesting findings, not conclusions. Let's go over their conclusion now. They find a clear log linear trend in memorization, while the model struggles to regurgitate strings which are repeated just a handful number of times. The probability increases dramatically as strings have more repetition. These small memorization values at low number of repetition corroborate the impact of training data deduplication on memorization observed by Lee et al. However, we find that memorization does still happen even with just a few duplicates. Thus, deduplication will not perfectly prevent leakage. While this relationship is perhaps obvious and has been corroborated for specific training examples, our results show that it holds across the entire training set and is not like just one small subset. Okay. So longer context discovers more memorization. Again, this is something which you would think of naturally as well, I guess, because in some sense, when you give the model more hints to generate something along one line, it will obviously in some sense be easier for the model to okay, I might figure out I saw this in the training data, maybe I should be predicting this. So the previous two questions evaluated how data collection and model training decisions impact the leakage of the model's training data when it is provided a fixed number of tokens. As a result, those experiments suggest particular actions that could be taken to mitigate memorization. However, even when the model is fixed, it is possible to vary the amount of extractable training data by controlling what prefix size you give. So by studying the number of tokens which impact extractability, they demonstrate the difficulty of discovering memorization. So again, let's go to figure 1c first, see for ourselves what they found. So when the context size becomes big, the extractability increases. But you see, this increase is in some sense saturating because the scale, and again, I guess, uh, as compared to the previous scale is on the x-axis, this scale is no longer log linear. So you can't just compare the model scale plot with the context size plot, but there's no point of this being log linear. But as you observe, the bigger the model, the bigger the context length, the more easier it is to extract. So let's now look at their results, what they've wrote. We observed that a fraction of extractable tokens increased log linearly with the number of tokens of context. For example, 33% of training sequences are extractable from the 6 billion model at 50 tokens of context compared to 65% with 450 tokens of context. Okay, did I make a mistake? Is this axis also log linear? I guess it could say so because this the scale is not exactly, yeah, the scale is you have a 50 jump, then a 100 jump, and then just a 300 jump, so it's a long scale. All right, we call this discoverability phenomenon. Also, sorry about all that stuff. We could not think of this as a log linear plot, which I mentioned earlier. This is a log linear plot. We call this discoverability phenomenon. Some memorization only becomes apparent under certain conditions with certain sufficiently long context. The discoverability phenomenon may seem natural. Conditioning a model on 100 tokens of context is more specific than conditioning on 50, and it is natural. However, the result is that strings are hidden in the model and require more knowledge to be extracted. From one point of view, it is good that some memorization is difficult to discover. This makes it harder for attackers, but or otherwise exploit memorization. Indeed, if a exact 100 token prompt is required, then in practice, no adversary, or like it is very rare for an adversary, unlikely for an adversary to do this. The difficulty in discovering the memorization also reduces the likelihood of non-adversarial training data regurgitation. For example, for GitHub Copilot, it reportedly rarely emits memorized code in benign situation, and most memorization occurs when the model has been prompted with long code excerpts similar to that in the training data. Practitioners building language generation APIs could significantly reduce extraction risk by restricting what prompt size they give to the users. But as you can see now, it's now the time of large prompts. Viewed differently, however, the difficulty of discovering memorization can also harm our ability to audit the models because existing approaches for provably correct privacy-preserving training of machine learning are applied only rarely in practice. It is common to attempt post hoc privacy auditing. Our results suggest that correctly auditing large language models will likely require prompting the model with training data, as there are currently no known techniques to identify the tail of memorized data without conditioning the model with large context. Improving upon this limitation is an interesting future work. Alright. So alternate experimental settings. So some other strategies which they could have used. So what if they did random data sampling? The majority of this paper uses subsets of training data that are explicitly sampled. We now explore what would happen if we instead choose a truly random subset. Specifically, they chose 100,000 subsets of length 100, 200, 500, and 1000 and prompt with the first 50 tokens and then test for memorization. If you look at figure 2 and 2D, we again see the size. So this plot basically, you again have the same trend with sizes, but this time through prompting the model with randomly sampled trays. As expected, the absolute probability of memorization is much lower in figure 1, where we prompted the model with training data from the sampled duplication normalized uh, subset, because here you could be missing out on a lot of sentences, which would like come up in the duplication normalized subset. As before, we observe similar trends with models to learn context and larger models memorize more, training examples on smaller models, and much more than the baseline GPT-2 model that was not trained on a pile. Similarly, providing more context increases the likelihood and the In figure 2b, they're using the sequence length, prompt length of sequence length minus 50. We see that the longer prompts are easier to predict correctly. The baseline GPT-2 model is nearly twice as accurate on sequences of length 1000 compared to sequences of length 100. So when you have a very big baseline prompt size, so you only need to predict 50 tokens, so you have 950 prompts. So even if the data was not seen by this model, like in some sense, the data might be overlapping, but uh, it's not. It hasn't seen the exact same data for some parts. It can still figure out what to say. We can extract the last 50 tokens of the length 1000 sequence with nearly 7% probability for the largest GPT-J6B model compared to 4% probability of the smallest one, and both are larger than the 2% extraction probability for the 1.5 billion GPT-2 XL model. These results taken allow us to establish a lower estimate that 1% of the pile is extractable by 6B GPT-J but not by GPT-2 XL. Now, what if they went for alternate decoding strategies? So greedy is like just sampling the most likely one, but many language model applications use other strategies such as beam search to find the highest possible likelihood. To understand this, they compare greedy decoding with beam search in figure 2c. They find that using beam search with b equal 100 results in only slightly more extracted memorization. The average difference is just under 2 percentage points on average with a maximum of 5.6. Interestingly, beam search and grid decoding generated the same output 45% of the time. And then you also have random sampling where the next token is selected at random from the model's predictions. McCoy et al. Found that random sampling resulted in generated text with a greater number of novel n-grams. Since the goal of the study is to maximize discoverability and antithetical goal to maximize linguistic novelty, we do not uh, experiment using random sampling because it is not really useful in their case. But as you can see here, uh, if you have beam search or argmax, you find some sort of similar trend. So the decoding strategy is not very relevant. So it's not like this is only working because you have 3D sampling. Now, what if you use an alternative definition of extractability? So in their case, uh, the in their experiment, they report a sequence as extractable if the model's generated continuation is identical to the true suffix. This method is a loose lower bound. Consider two sequences x1, x2 both contain the training dataset. Suppose these two sequences share the same prefix and differ only in the final suffix. When we select x1 and prompt the model on the prefix p, we will report a success only if the output equals s1 and not if it equals s2, even though this is also a form of memorization. Now they are considering how our results would change if they instead checked that the generation from a prompt P was contained anywhere in the training dataset. This gives a slightly larger measurement of memorization, and by comparing these two methods, they can see how much the choice of measurement affects the result. So searching within the entire dataset finds more memorized content because you'll have that substring with some other prefix somewhere. For example, at 100 repetitions, 32.6% of outputs are contained somewhere in the dataset, but just 15.8% match the ground truth continuation. This difference becomes more pronounced as the number of repetitions increase. The maximum difference is 28.4% at 2,200 repetitions, as you can see in uh, this plot right here. Obviously, because the entire dataset, 800 gigs, might have some substring which the model generates somewhere. We refrain from using this approach because the definition requires vastly larger computational resources. It requires querying hundreds of thousands of sentences. Therefore, to promote reproducibility, they continue with the generated one. Now they're looking at qualitative examples of memorization. We now turn to training sequences memorized by models. So figure 6 in the appendix shows examples of sequences. We found that most of these universally memorized sequences to be unconventional, like codes, limits, or highly duplicated text such as licenses. More interestingly, table 1 summarizes the total number of sequences that are memorized by one model but not another. Interestingly, model size leads to larger number of non-overlapping memorized sequences, although every model has some amount of memorization not shared by other models, even the 125 million one. Alright. In figure 3, we present qualitative examples that are only memorized by the largest 6 billion model. We highlight some interesting patterns. While the generations from the smaller models do not match the training data, they are generally thematically relevant and locally consistent. However, a closer inspection reveals that each generation only syntactically sound but semantically incorrect. Appendix C contains details of experiments along with example of sequences which are memorized by 6 billion parameter model despite only being repeated a few times. These tend to be easily completed text. We also presented figure 12 examples which are repeated thousands of times but are surprisingly not memorized. Many of these are correctly completed but only differing on semantically unimportant characters, which is not considered as memorization because they have a very tight definition of exact overlap. So let's look at table one now. So you can see uh, these are examples which are memorized by 6 billion models but not by others. So you can see that the 2.7 billion model is somewhat correct. For code, surprisingly, I guess this is, I'm not sure, is this code? I guess it's just a JSON. Let me see. This looks like CSS. This is CSS. So the models are surprisingly close in this case, but in others it is not the case. Here you can see the 2.7 billion model is somewhat coming to starting off on the right track at least. So replication study. The above analysis represents convincing evidence that memorization skills and log in a relationship. We now replicate this analysis of different language model families trained on different datasets and with different training objectives and perform the same memorization analysis. So you have the T5 family trained on C4 and language model from Lee et al. Trained on deduplicated C4. We expected a result to cleanly generalize, and this was indeed the case for molecule, yet we found the situation to be complicated when considering training data duplication. So if you look at T5 MLM, right. So the T5 version 1.1 models are mass encoder decoder models trained to reproduce spans that were randomly deleted. The models vary in size from 77 million to 11 billion parameters. These models were trained in C4 and which is 800 gigs of data. At 11 billion parameters, the largest T5 model is the largest publicly available mass language model. Mass language models making these T5 models a good candidate for studying how memorization skills in model size. They must first define what is extractable data for MLM tasks. T5 models are trained by removing a random 15% tokens from each training sequence in IID. Uh, uh, IID is independent. I just forget what. So basically, it basically means your training data identically and independently distributed. Yeah. And the model must then fill in the blanks to restore the tokens which were dropped from the input. As a result of this different training objective, definition 3.1 is not applicable because there is no prefix. You have basically a sequence where you have to fill in the mask. So they define a sequence as memorized. If the model perfectly solves the MLM task from that sequence, for example, for a 200 token sequence memorization, the model can use 170 tokens to perfectly predict the remaining 30. Because the token dropping process is stochastic, it is possible that one set of dropped tokens might yield an output while others might not. For simplicity, they inspect only one set of randomly masked tokens per sequence, but we are already arguing with 50k sequences, so this randomness should not harm the results. They are able to reproduce the model scaling, uh, and they find show this in figure 4a. So as you see, the larger the model, the more data extractable it is. Increasing the number of parameters similarly increases the ability to solve the prediction task. Surprisingly, when the overall scaling trend holds true, we discover an order of magnitude less data in mass language models than is comparably sized causal models. So if you look at the 3 billion T5 Excel, it just memorizes 3.5%, repeated 100 times, while 53.6% of sequences repeated 100 times in Memorize in GPT Neo 2.7b with context length 150. We believe, without evidence of course, that this difference can be explained because the choice of tokens to mask at training time varies for each duplicate of a training example, while in causal language models they always have the same task. Got it. This seems like a fair hypothesis. Next, we turn to reproducing the analysis on the effect of duplicate examples in the model's training data. The situation here becomes significantly less clear, as you can see in figure 4b. While sequences which have been duplicated more often are easier to memorize, there is not an obvious log-linear relationship. In particular, compared to the smooth curves in GPT-NeoPile combo, they couldn't find this for T5 sequence. Even more surprising is that the variance is statistically significant. Sequences repeated between 159 and 196 times are memorized with probability no more than 5.1%. However, the sequences with 138 and 158 are memorized at least 6.2 with probability at least 6.2%. That is, for some reason, sequences that occur approximately 140 times are more likely to be memorized despite occurring less often. In order to explain this counterintuitive phenomena, we qualitatively study each of these buckets of example. Surprisingly, we find most of the duplicate example contained in the 138, 158 bucket are mostly white space tokens, making these sequences much easier to predict correctly than sequences found at the repeat count. This effect, to a lesser extent, can be found in the buckets, which contain many approximately near duplicates, which is what gives you this sort of kink pattern, I guess. You don't have like a clean scaling up like thing. Alright. Language models trained on deduplicated data, model and dataset. So they're using Lee et al.'s 1.5 billion parameters for the language models, which was trained on C4. One model trained on a version of C4 which was deduplicated, and one which was not, uh, and one model trained on a version of C4 that was. Alright, sorry. So you have C4 which was reduplicated by removing all documents which were near duplicates, so I guess locality sensitive hashing or something of that sort. And one model trained on a version of C4 that was deduplicated by deleting any string of length 50 that occurred more than once. They found that both types of deduplication reduce the likelihood of memorization. We were most interested in whether models trained on deduplicated data would still exhibit increased memorization. In 4C, you see these plots. We find that models trained on deduplicated datasets memorize less data than models trained without deduplicated datasets. For example, for sequences repeated below 35 times, the exact deduplicated model memorizes an average of 1.2% compared to 3.6% without deduplication, a statistically significant increase. Second, while deduplication does help for sequences repeated up to approximately 100 times, it does not help for sequences repeated more than this. We also observe a spike beginning at 408 repeats. The extractability of the small spike is larger than any value before the spike. We hypothesize that this is due to the fact that deduplication strategy is necessarily imperfect in order to efficiently scale. Thus, while it may be possible to remove most instances, different and valid definition of duplicates can mean deduplication is not exhaustive. So going back to the plots, you can see there is this spike which they're referring to, which they're like alluding to might be due to not perfect deduplication, and this falls down and then this rises up again. So based on repetition, you have an increase in extractability with that spike. All right. So now the conclusion: our paper presents the first comprehensive quantitative analysis of memorization in LLMs by directly reprocessing the training data. So they have two broad conclusions. For those who study generalization, we have shown that current language models do accurately model the distribution of the training data. This does not necessarily imply they will model the desired underlying data distribution. In particular, when the training data distribution is skewed, that is, it contains many duplicates, larger models with more capacity are likely to learn these unintended data peculiarities. It therefore becomes even more important to carefully analyze the dataset used to train even larger models, as future models are likely to remember more stuff by these scaling laws, of course. For those who study privacy, our work contains the indicates that current large language models likely memorize a significant fraction of the data. Memorization skills log linear with model size. By doubling the number of parameters, we can extract a significant larger fraction of the data set. Given that current SOTA contain more than 200x as many parameters as the largest 6 billion parameter, we analyze it is likely that these larger models memorize much, much more. At the same time, we have shown that memorization is often hard to discover, and for an attack to extract, they will need to develop qualitative linear extract strategy because you, for a thousand length prompt, you don't have the 950 thousand length sequence. You are very unlikely to have the exact 950 starting tokens. Fortunately, it appears that training data inserted just once is rarely memorized, and so deduplication is a good strategy. Alright, so for the acknowledgements that have alluded her, then Catherine Lee's research is sponsored by Cornell, and then Daphne Filito's research is sponsored by DARPA, and so forth. Alright, now the contributions, and yeah, that's the paper. It was a really cool paper, interesting findings, and it was very well written. I'll be going over a bunch more of memorization papers in the near future, so be on the lookout for that. If you want any papers to be recommended, which I should cover, drop a message. Thank you for tuning in. I'll hope to see you again next time. Also, I'll just go over the appendix once to see if there are any interesting things that we should be looking at. There are a lot of examples which I'll be looking at in my free time, but I don't want to bore you guys with this stuff. So, thank you.